My name is Marcel, and I'm a shell, and today I'm going to be talking about microstates, but please bear with me because I'm not a physicist. I'm just a shell with shoes on, thank you. So today's problem deals with two atoms, one with two oscillators and one with just one oscillator. We want to find the total number of microstates and the entropy corresponding with the system, knowing that there are 50 quanta of energy dispersed within the system. We also want to make plots of the number of microstates and the entropy, so that'll be fun. We're going to use Microsoft Excel for this because a friend of mine tried to do it by hand and they about died doing it, so computer it is. In our first column, we have Q1, which stands for the amount of quanta of energy in the first atom. We have all the possible quanta per atom here, so atom 1 could have no quanta, while atom 2 could have all 50 of them, or they could split the energy with one atom having 16 and atom 2 having 34, so on and so forth, as you can see. As while one column has increasing quanta, the other decreases. And so Q2 should be pretty clear for you at this point. If not, I'm sorry, but I have to move on. I'm a very busy shell. In column C, we have omega 1, which is the number of ways the quanta of energy in atom 1 could be distributed in its two oscillators. Therefore, omega 2 is the number of ways the quanta of energy in atom 2 could be distributed in two oscillators. The way we find omega for both atoms is the same, which is through an equation that states omega equals q plus n minus 1 factorial divided by q factorial times n minus 1 factorial, where n is the number of oscillators in the atom. So as you can see, we apply the equation to our first atom and see that the number of ways is equal to the quanta of energy in atom 1 plus 1, and the number of ways the energy can be dispersed in atom 2 is just 1 because there's only one lonely oscillator. Makes me cry every time. So then we find omega total by multiplying omega 1 by omega 2, and omega total essentially has the same values as omega 1 here. And because we want to find the entropy associated with this system, we use the equation S equals Boltzmann's constant times the natural log of omega total, which we plug in up here, right there, where Boltzmann's constant is 1.38 times 10 to the negative 23rd, and then we multiply that by natural log of Q1, and we find all these nice values for entropy. And if we graph it, as in graph entropy versus Q1, we can see that our entropy actually decreases the greater the amount of energy we have in atom 1. And if we just look at the graph of omega total versus Q1, we can visualize the probability distribution of finding a certain microstate in a certain configuration. We see that as Q1 increases, the probability increases because more quanta of energy are concentrated in one place. Another way of saying this is that the greater the number of ways to have energy in a microstate increases the probability of having energy there due to more quanta and more oscillators. And so that concludes my video. I'm afraid I have to go now, and I have to walk my dog, which is just a piece of lint tied at the end of a string. But I hope you learned something from this, and I will see you all next time. I also forgot to mention that the total number of microstates possible is 1,326, so there's that. Okay,